module 1 to 4, module 1 was basically on recap. Module 2, 3 and 4 were primarily about kinetics and thermodynamics and mechanisms. So, what do you mean by kinetics, how does thermodynamics play a role, and how do you get from a detailed mechanism, what happens at a molecular level, to a rate expression that you can use for various things. You can use the rate expression for analysis of the system, you can use rate expression for design of the reactor, and so on. Okay. So, that was what we did in modules 2 to 4. Modules 5, 6 and 7, we are going to look at a mesoscopic level. Okay. So, what we mean by mesoscopic level is we would look at, when it comes to a solid, we would look at a solid particle. When it comes to liquid-liquid reactions or gas-liquid reactions, we will look at a gas bubble or a droplet within a system. Okay. So, that is what we are going to look at. So, this is going to be a small part of the entire reaction system often. Okay. So, we are going to zoom in onto that small part, which could be again a solid or a liquid or a gas, and then we are going to say what are the processes that are taking place in that particular system. Okay. So, in this module, so that is module 5, 6 and 7. Module 5 is going to deal with solid particles. Okay. Solid particles that are typically catalytic in nature. Okay. Not, it does not necessarily have to be catalytic. The discussion that we have is going to be a little bit more general, but essentially this discussion has traditionally been applied to catalytic systems. So, let us say you have a porous catalyst particle. What happens within the catalyst particle, what are the processes that are taking place, what happens just outside the catalyst particle, what are the processes taking place, and how do they relate to mass transfer and reaction. That is what we are going to do in this module. This module has two parts. The first part is external diffusion, the second part is internal diffusion. For your quiz, parts up to the external diffusion will be there for your midterm exam. Internal diffusion will not be there for your midterm exam. We might be able to finish internal diffusion by midterm, but we will not include it in the exam. Okay. So, the first half of this module is what we will have for your exam. Okay. So, let us go and get started with this. This material module derives material from chapter 3 of Froment and Bischoff and chapter 6 of Davis and Davis. Okay. So, let us recap the notations that we have used. We have used capital C to represent concentration, the subscript A, B, X, K to represent what species it is. Okay. So, this is what we have used. So, when we write it as Ck or Ca, this basically means concentration of A at various different points in the overall system. Okay. So, this could be within the reactor, at the inlet of the reactor, at the exit of the reactor, and so on. So, this would be a property that will vary with Z, R, T and whatever else might be. Okay, let us say Z, R, T. Okay. So, this is a concentration that would vary with this. So, Ca is just generally which could vary with various different locations. Okay. Now, when we are talking about a catalyst particle, okay, we have the catalyst. So, let us look at a catalyst particle. Okay. The value of concentration over here, we will represent this as Cab. Value of the concentration at this point at the surface, we will represent this as Cas. Okay. And let us say that this is a pore that goes in. Okay. The concentration will change along the radial direction, and that is just, I will just represent as CAR. Okay. Now, let us say that this particular thing is in an entire reactor. Okay. The concentration would change with location as well. Okay. This is something that we are not going to consider in module 5, 6 and 7. We will bring it up in module 9. At this point, we are not going to consider that. So, at this point, we are not considering what is happening within a reactor. We are taking, say a microscope or whatever, a zoom lens, and just zooming in around a particle. Okay. That is what we are doing in module 5. In module 6, we are also again going to zoom in around a particle, but it is a particle that is also reacting, and therefore, the nature of the particle is changing. In catalyst, the nature of particle does not change. So, module 5 is where the nature of the particle does not change, module 6 is where the nature of particle changes, and module 7 we are going to cover gas liquid reactions. So, it is going to be a liquid droplet falling in a gas or a gas bubble rising through a liquid. Okay. So, this is what we are going to cover in the next 3 modules, and again the idea is the same. C, capital C is concentration. All of the concentrations will be in terms of moles per liter or moles per centimeter cube or moles per meter cube, whatever it would be, it is going to be in moles per unit volume. Okay. Concentration of adsorbate on active site, this was what we did in module 4, that is in terms of moles per centimeter square or moles per meter square of catalyst. Okay. Same as this. Okay. And what we had said earlier is our Ca star multiplied by gamma. Okay. Again, for like 2 minutes in one of the previous lectures, I had said that this is valid only when species A is occupying only one site. There are several cases where a species occupies 2 sites. This particular equation is not valid under those conditions. So, in your research, if you come across those conditions, only then this particular thing is not valid. As far as this course is concerned, you can safely work with this equation. We will not consider cases where one species is simultaneously sitting on 2 sites. So, a species sleeping on, let us say, okay. So, you have C and H simultaneously sitting on this side. This type of case we are not considering in this course. This case happens, it happens quite a bit in types of systems that we are looking at these days, okay, but we will not consider in this course. All the things that you have developed in this course, all the things that the analysis tools and all that will be applicable to these types of systems also. The equations are going to be different because the nature of adsorption is different, but other than that, the process, the procedure, the way you analyze it, if you want to think of it as an algorithm, that remains the same. Okay. But beyond this, I am not going to repeat this too many times. So, for now you can assume that for module 4, whenever a species sits on a surface, it sits on one particular site at a time. Okay. Just recapping the various processes taking place in the system. Okay. So, let us look at basically some reaction taking place in the reactor. This could be, let us say, water gas shift or whatever it might be. Water gas shift, you can safely represent it as A plus B going to P plus Q, where A and B would be CO and H2O, P and Q would be CO2 and H2O, and any reaction you can you can consider. So, you have certain species coming in, certain species going reacting, diffusing, convecting and so on, and reactants plus products, unreacted plus products formed plus side products will be coming out of this reactor. Okay. But if you look at any location within the reactor, the concentration of all the species is going to change along the length of the reactor. Okay. We are not talking about moving along the length of the reactor, we are taking a binoculars or a zoom lens and focusing only on one small section. Okay. In this small section, if you zoom in, this is what is happening. You have the gas that is flowing far off. Let us say you are, think yourself as an amoeba, small amoeba sitting on the surface of the catalyst. As far as the bulk convection is concerned, it is too far away from you. Okay. Yes, it is happening, but it is too far away from you for you to really feel it. You know that it is happening. Okay. Just the way if you look up and you see a aircraft flying, you know that the aircraft is flying, but because of that aircraft flying, whatever changes in the wind that happens, it does not reach you. Okay. So, all of the convective processes are that far away from you. Okay. So, what you are actually seeing on the surface over here is the reactants reaching the surface because of diffusion. Okay. Products going from the surface because of diffusion. Okay. This is what we call as external diffusion. Okay. Thereafter, this particular AS, CAS, the A that is sitting on the surface will diffuse inside the particle, it will reach the active catalyst surface, the reactions will take place. How will the reaction take place? That is what you have been discussing the entire last week. Okay. The reactions takes place, products are formed, the product will diffuse back to the surface. So, this diffusion of A into the pore and the diffusion of P to the surface is internal diffusion. Okay. And the reactions are the ones that take place on the surface. Reaction taking place on the surface, we have already done that as a part of module 4. External diffusion is module 5A, internal diffusion is module 5B. Okay. This okay. Okay. So, let us think about particle and reactor level aspects of this. Okay. So, let us say that this is a packed bed reactor. Okay. You have your reactants coming in, you have this particular thing filled with catalyst particles. Okay. Now, let us say again for argument's sake, let us say the concentration of the reactant starts from some inlet concentration and keeps falling to some exit concentration. Okay. For argument's sake, let us say it starts at 1 and it ends at say 0.2, 10% conversion, well not necessarily, sorry 80%, not necessarily. If this is mass mole fractions, then that is not the conversion. If it is molar flow rate, yeah, that is the conversion. We have talked about that in the first week of this course, right. But anyway, so the concentration falls from 1 to 0.2. Okay. Now, let us look at this particular point. Okay. The concentration over here might be say 0.85. Let us look at this particular point. The concentration over here might be 0.55. Concentration here is 0.3. Okay. How that concentration varies is something that you do at reactor level. Okay. As I said earlier, we are going to zoom in over here, or maybe I should have put this point over here. We will zoom in over here and try to find out what is happening with the catalyst particle and at this point. Okay. So, we are going to talk about, so this is the catalyst particle, this is that particular point. At this point the concentration is 0.85, okay. Because this is a reactant, the reaction is taking place either on the catalyst particle or the reaction is taking place within the catalyst particle, okay. Let us look at the point over here. This has a certain other concentration, okay, and let us say for argument's sake this concentration is 0.81. Okay, do not write these numbers, these are absolutely arbitrary numbers. Okay. Okay. The concentration is dropping. Why is the concentration dropping? Because the reaction is taking place. The reaction might be taking place on the particle or reaction is taking place within the particle. Okay. Let us say we do not care where the reaction is taking place, we will talk about that in module 5b. Module 5a, we are talking about what is happening. We have diffusion that is taking place. Why is the diffusion taking place? If there was no reaction, the concentration over here would be 0.85 itself. There will be no reason for diffusion to happen. Why does the diffusion happen? Diffusion happens because the concentration is lower. The concentration is lower because the reaction is taking place. Okay. Now notice there is no reaction taking place in the bulk. Okay. There is no reaction taking place in the bulk. Okay. In reality, what would happen is that the concentration would be changing from this point to this point. Okay. What we will do, what we will assume is that we will assume that there is going to be a small film around it. Okay. And we will assume that the concentration will change only in this film. Is this really true? Maybe, maybe not. Okay. In reality, it is not absolutely true. Okay. But it is a pretty good approximation. Okay. Why is it a good approximation and all that? We will come to that. Okay. Now let us look at if this particle was porous, what is going to happen? Okay. Let us say this is the pore. Okay. Now this guy diffuses inside. Okay. Let us say there is a catalyst over here, there is a catalyst over here, there is a catalyst particle over here. Okay. As it diffuses, reaction takes place here, reaction takes place here, reaction takes place here. Okay. So the concentration might change 0.80, 0.79, 0. Or 0.79, 0.78, 0.772, something like that. Okay. So the concentration is falling as you go inside the catalyst pellet. Okay. Within the pellet, you have reaction plus diffusion taking place. Okay. So now there are two differences between external diffusion and internal diffusion. Difference number one is external diffusion is completely a molecular diffusion. You have the molecule just diffusing in rest of the gas or rest of liquid. Okay. Within the pore, there is a pore diffusion. A pore diffusion is affected by both molecular diffusion as well as something called as Knudsen diffusion. Okay. We will come to that when we start module 5b. Okay. So that is difference number one. Difference number two, and that is another quite significant difference, is in the bulk, external diffusion is taking place without reaction. In the catalyst particle, the diffusion is taking place accompanied by reaction. Okay. So, there is no reaction taking place in the bulk, there is reaction taking place in the catalyst surface. Okay. The final thing that we are going to assume in the bulk is whatever convection and all that is there, that convection is going to take place over here, it is not going to take place within what is called as the film or the boundary layer. Okay. Is it true? Not really, it is a reasonable approximation. Okay. A reasonable approximation that allows us to do a whole lot of analysis in a much more lucid and much more simpler manner. Okay. And again the analysis at an individual particle, okay, this bulk diffusion taking place, what we are going to say, we are going to form a film over here, okay, and all of the diffusion will take place in that film. Okay. The film thickness, we will take it as delta. Okay. Keep in mind is delta is our imagination. Okay. It may not exist. I am using the word may not, I am not saying it does not. Okay. There are some cases where a film does actually exist, okay, but for the most part it is something that we are going to use in order to simplify our analysis. Okay. But because this delta is something that you cannot measure, we will replace this delta with some kind of L or D or LC or DC, which is called a characteristic length. Okay. What does characteristic length mean? Characteristic length means it is a physical feature of that system that you can either design or measure. It is something that is convenient to use. Okay. It is not something that is always guaranteed to be that this is how it scales. Okay. Now, for example, let us think about a spherical catalyst particle. Okay. The characteristic length in case of catalyst particle is its radius or its diameter. Okay. So, think about the external film. The external film is outside that radius. Okay. So, that delta lies outside that radius. Okay. Now, how much is that delta? The delta is typically small. Okay. So, if you think about r plus delta, you can say it as approximately equal to r. Everything scales with delta, the delta scales with r. So, therefore, with a lot of research and with a lot of analysis, we have found that radius of the particle is a reasonable characteristic length. So, if it is a spherical particle, we will take capital R as the characteristic length. If it is a slab, thickness of the slab we will take as a characteristic length. If it is a tubular reactor, remember I had talked about for example, a monolith reactor. So, you have channels that are say 1 millimeter in diameter or 0.9 millimeters in diameter, we will take the diameter of the channel or the hydraulic diameter of the channel as the characteristic length. Okay. Again, what characteristic length is closely related to what expressions that you are going to use in order to analyze the diffusion processes. Okay. But it is a choice that we have made for convenience. Okay. If you change that characteristic length, everything just scales by a factor. That's all that is going to happen. Okay, so if you change the characteristic length from radius to diameter, everything is going to scale by a factor of 2 to the power whatever, depending on what expression governs that particular behavior. So, for example, when it comes to external diffusion, it is going to be 2 to the power minus 1, because for various reasons we will come to that later. When it is going to be internal, it is going to be a little bit more complex, because there is going to be this concept of Thiele modulus and so on that will come in, which we will talk about next week. Okay. So, that is what it is about. So, let us be aware of where all of these come from, okay. But as far as we are concerned, what we are going to do is we are going to use a characteristic dimension or a characteristic length that is convenient for our analysis, okay. And when it comes to the expressions that we are going to derive and use, okay, those expressions will be related to the characteristic length that we have chosen for that analysis. Okay. That is something that when it comes to the derivation as well as using those expressions, we will make them explicitly clear. Okay. So, that is going to be the overall focus over the next probably 2.5 lectures and tutorial. Any questions so far? Okay. So, let us talk about diffusion. Okay. Now, let us think about situation. Let us say that you have 10 red balls, 10 blue balls. They are there in a box. Okay. Let us say that the box was delivered to you. Let us say that box came from New Delhi. It came through a courier. You look at that box. The box is not, you know how couriers are, right? There are some holes in the box. There's, you know, some dents, dings in the box, and so on. And that's how that box has come to you. Okay. Now that box contains 10 red balls, 10 blue balls. Okay. What is, I am not asking you what is the situation, I am asking you what is the more likely situation. Okay. The box got shaken, maybe not, definitely not stirred. Okay. What is more likely situation when that box arrives to you? Okay, it is not fully filled. I mean, if you shake it, you can see the balls moving and all that. Why? Sorry? Number of microstates are more in second one. Okay. So probability will be more. What else? Probabilistic argument. Anything else? Yeah? Say, okay. What else? Balls will have some tendency to move here and there. Okay, so that this ball will move here, come back over here. This ball will move here, come back over here. But again, instinctively you didn't think that way. His answer is statistical mechanics. All of your answer is entropy. That is essentially what entropy is. Entropy is disorder, right? You yourself chose disorder. Why? Because that is how you have experienced or we have experienced the world around us. Okay? So, you instinctively you understand entropy. If you ever thought that I didn't understand entropy, this is a live example of you demonstrating your understanding of this fuzzy concept of entropy. Okay. If there are 10 red balls and 10 blue balls separated, that means somebody who has done that separation, somebody has filled those 10 balls, put it in a box, and those balls did not move during that transportation process. Maybe it was really jam packed and therefore it did not move. Okay. So, if it did move, okay, they will be very well mixed. Okay. The balls naturally won't go from the right hand side image. I do not know whether this is right. Yeah, this is right only for you. The ball will not naturally go from right hand side image to the left hand side image. To go from right hand side image to the left hand side image, you need to add in energy. How do you add in energy? You go there and you pick those balls. That is what you do. Pick this ball, take it over here, pick this ball, take it over here. After that, you will have that separation. What we are defining in this particular process is exactly what is the fact that entropy always increases, decreases, blah blah blah, you can never change. No, it can. You can change entropy by moving the balls. Okay, but if you do not add that energy, then it will go towards disorder. Okay. Disorder is the right hand side image. Now, let us say you are the one doing the packing, you are not the receiver, you are the ones who did the packing. So, you put the 10 balls on the left hand side, 10 balls on the right hand side. Okay. Let us say this particular courier person is a very careful courier person. Why? Because you have put fragile handle with care on it. So, that person, I have not ever seen a courier do that, but let us assume that you yourself are a courier and you are the one taking it, bringing it to me, and you bring it carefully. What do you think? How do you think the balls will be? Still separated? Maybe you are bringing it carefully on your bike and suddenly there is a big pothole, your bike does once. What is going to happen? A little bit of mixing. Okay. What if you shake vigorously and what will happen? More well mixed. Okay. That is what temperature does. Taking it carefully basically means doing it at low temperature, little bit of potholes, slightly higher temperature, lot more potholes, much higher temperature. Okay. The first aspect, right versus left, was about thermodynamics, how fast they mixed, is about kinetics. Okay. And that mixing process is diffusion. Rate of diffusion is going to be proportional to temperature to some positive power, whether it is 1, 1.2, 1.5, 15, 0.15, we will see in due course. Okay. But it is closer to t to the power 1, that is what you would instinctively feel, that is what you have instinctively answered. Let us see later on whether the instincts are correct when we talk about molecular level or not. But essentially what we have said in the class, what we have defined in the class, not me but you guys, is this is what entropy is, this is what the thermodynamic picture is, this is how they will move to eventually equalize. Okay. Now, let us say that everything is equalized and the image is like right hand side, okay, but the person has still not yet reached our home. Let us say that person is still on a bike riding, very miraculously through the roads from Kanchipuram and so on, coming through Porur, Punnamari and reaching us over here. Let us say at Kanchipuram itself the blue and red balls are well mixed. Okay. The person then finally reaches you. Do you think in that particular process the blue and red balls haven't moved? They are still moved, right? But does the snapshot in Kanchipuram look different than snapshot in Chennai? It is coming from Bangalore. the snapshot would look very similar, right, statistically very similar, though the actual positions of the balls might have changed, but the balls are very well mixed is something that remains whether in Kanchipuram or in Chennai. Bangalore the balls were separate, by the time they reached Kanchipuram the balls got well mixed, by the time they reached IIT campus the balls still remained well mixed, okay. But between Kanchipuram and Chennai or IIT campus the balls are still moving, they are still mixing, okay, but the rate at which the blue ball is moving from left to right is exactly matched by another blue ball going from right to left, okay. So they are all very randomly moving, so the net motion once it is fully well mixed is 0, okay. Does not mean that they do not move, it does not mean that suddenly all those balls got frozen in place, they did not, they were still moving, the effect of that motion is not seen, okay. This is essentially what happens over here, okay. When we say, is there a question? Okay. When we say that the concentration of A is 0.85, concentration of A is 0.85 over here, it is not that the molecules of A are not going from bulk to the surface or molecules of A are not going from surface to the bulk. The number of molecules coming from the surface to the top of the film to the bulk and from bulk to the top of the film are evenly matched, okay. Not so within the film. Why not so within the film? Because there are more blue balls as a fraction on the top of the film than there are blue balls as a fraction on the bottom of the film. So there is 100 blue balls coming in, 96 blue balls going up, so net is 4 blue balls, okay. From the bulk to the top of the film 100, from the top of the film to the surface 196, okay. That is our imagination, okay. Where does this difference of 4 get accounted for? This difference of 4 gets accounted for the reason why concentration is falling in this direction, okay. That is how it accounts for, okay. So that is about diffusion. So hopefully okay. Even if you did not know chemistry, even if you did not know chemical engineering, even if you had not done undergraduate, you still intuitively know thermodynamics, you still intuitively know kinetics. Now is our task to convert that intuition into mathematical equations and analysis, whether it is mathematical or understanding based, that we can then use for various purposes. That is the purpose of this course. Okay. So, that brings us to the idea of species flux. In this particular case, what I talked about, 100 minus 96 is the species flux. The species flux is the net flux, which is 4.04 in this particular case. Okay. So, the overall balance from module 1 that we had gotten. Okay. This is the species balance that we had developed. Okay. Remember the analogy that I had given about first standard kids and 10th standard kids in a bus. Okay. This is a bus that is moving. The overall movement of the red kids and the blue kids, because of the net movement of the bus, is captured in the convective term. Okay. The movement of the blue kids in relation to the bus and the red kids is captured by the diffusive term. Okay. Fick's law basically says that J is proportional to concentration difference okay, and flux is in the direction of high to low. Okay. Proportional to concentration difference basically means C at this location minus, or C at this location minus C at this location. The direction is inverse to, so the direction is in the direction of decrease of concentration. Because the direction is in the decrease of concentration, you get the negative sign by sign convention. Again, we had talked about that 4 weeks back. Okay. And the fact that it is proportional to the concentration difference is going to give us a del C by del Z type of a term. Okay. So, this is how we can write the molar, the mass flux. The molar flux is going to be okay. So, this is how all of this is going to be. Nk is okay. So, if you could actually measure how fast the molecules move, okay, you will not need the whole thing about diffusion. The reason why diffusion comes in is because what you measure is a mass averaged velocity. You are not able to measure the molar velocity, the actual velocity with which the red and blue move. Okay. When it comes to humans, when it comes to the picture of 10 standard, first standard kids running in the class in a bus, those are of the size of how we perceive nature. Okay. So, if I ask you to track an individual blue boy or an individual red boy, you will be able to track him or her, boy or girl. Okay. But if those are molecular, you cannot track individual, you can only track the average motion. So, that average motion is the convective part. Okay. The difference between the individual motion and the average motion is the diffusive part. Okay. That diffusive part, through a whole lot of research and through a whole lot of experimentation, and over the last 60-70 years through a whole lot of modeling, we have now pinned it down to what are the factors that it depends on. Well, that is where two laws come in, the Fick's law and Stephen's law. Fick's law is going to talk about diffusion under dilute conditions, or diffusion when it is binary. Stephen Maxwell's is going to be about multi-component. Thereafter, we are going to talk about special case of dilute mixtures and multi-component and how those are equivalent. And then, so that is what we are going to do in the first half of tomorrow's lecture. In the second half of tomorrow's lecture, how we can use all of these concepts to look at external diffusion in a catalyst. So, that is going to be what we are going to do over the next 2 days. Okay. Alright. So, today it was mostly setting of the stage. Please read ahead, the notes are uploaded. So, please read ahead and come for the next lecture. Okay. Thank you.